So I'm Frank Lind. I'm the Deputy Research Director for those students who don't know me. I think, did we just get a whole nother? Oh, we did. All right, go away. Okay, don't go away. Can I just do that?
Yeah,
there we go.
Let's try that.
Let's try that. And so I'll give a little bit of an overview of the flagship projects, but mostly we're going to try to get to Mary, who's going to talk about our VLA experiment. And then that's going to set the context for all the wonderful work our team has done. And the work element leads are going to come up. Boy, this is going to be fun. I can just tell. Thanks, sir.
Great.
Okay. All right. All right, flagship projects, you know, there's significant investments by the center. We pivoted to them a little over a year ago. I'm just gonna, keep up. There we go. You know, the idea was to have some policy-driven research efforts that were more coordinated than had been happening in the center. You know, there was a process by which we came up with these projects via the research planning committee and a lot of input from everyone and many of the people in the room. And, you know, we staffed these projects with a combination of the faculty, but also we brought in some key areas, research professional staff from some of the organizations like Haystack who have them. Mary has been helping us as our project manager to really kind of drive things forward on a regular basis. So there's two flagships right now. Today you're going to hear about Flagship 1. Tomorrow you're going to hear about Flagship 2. Flagship 1's kind of been executing for a year, so there's a lot of results. Flagship 2 is really just getting its funding and getting going. There's been a few ongoing activities for Flagship 2 for year 4, but mostly it's going to be in year 5. We really have a big swath of the SpectrumX Center engaged, and you know, some of this stuff is really starting to make its way out into the world. We've got a bunch of GitHub repositories where things are showing up. I think there'll be more of that. You know, I think it's very exciting. We already have people wanting to buy things. I'm actually pretty impressed with the number of requests I've been getting. Okay, let's see. Can I get this to go forward? Okay. Spectrum awareness is really the theme of Flagship 1. It's to enable next generation sensing awareness and ultimately understanding at scale. It takes a lot of infrastructure of hardware, software, radios, antennas, people, knowledge, students who can go do things. To really make something like this happen. We've been really trying to create a demonstration of the possible. And I think with our first VLA experiment, I was very excited by how well that demonstration of the possible went. And I'm really looking forward to what we're going to do this year in extending some of the things that were very much, I would call them alpha prototypes and beta prototypes from year 1, you know, our first year of this, into things that are much more mature and effective as we go into our next set of experiments. Underneath it was to try to engage students with really unique experiences. We often have very interesting radio facilities, say at NRAO. There's other ones around the world like NASA and NOAA facilities. And by focusing our experimental efforts, you know, around a particular band, in particular, this initially was from the National Spectrum Strategy. We survived the big beautiful bill, so the lower 7 to 7.5 gigahertz made it in. I happened to end up on 7.125 gigahertz for our first license, so we ended up like hitting the bullseye right on. This is letting us make focused measurements that are it's turning out extremely relevant to upcoming policy decisions. So we really kind of did the right selection. And we're focused on active experiments and passive coexistence. So we're not just going out and measuring the spectrum. In many cases, we're constructing experiments to experimentally transmit our own signals, do interesting coexistence experiments with them, and then see what we can understand from the data that we take. You'll hear about work packages and work elements. We're going to hear from every work element lead here shortly. So this is how they're organized. These are the categories in different areas. Mary's going to talk about the experimental demonstration and analysis. We're going to hear about data infrastructure from our Notre Dame research computing folks. We've got some modeling rights and policy that you'll hear about. And then we've got our sensing measurement platforms and our AI algorithms that you'll hear a little bit about. And I'm really, you know, hoping that as, you know, we're going to have a planning workshop on Wednesday. We're going to really focus on how to integrate these things and get our students involved in these field experiments coming up over the next year. This was our timeline that I put together a year ago. We're on time. We've done the things on this chart up to where we are. In fact, we're a little farther along in some of these things than Q4 2025, early 2026. So student data competition, Cong, thank you. Laila, adaptive array demonstrator. It's pretty close. Yeah. You're gonna get there. Yeah. And we've got some really exciting stuff with our next generation platforms coming in the next year. Sudhakar's been working hard. I've been actually looking at how to integrate our reference platforms. And we're about to take some of the things we've done this year and really extend their capability over a broad swath of wireless and hopefully into a center renewal. Flagship experiments, we've implemented a number of interesting experiments. You'll hear about some of them today. We're now going to have the student competition looking at the VLA data, which I thought was an exciting way to leverage that data set. And then we've got some work to do in coordinating some of the upcoming experiments. There have been things people have said they would do in the community that have slipped a little bit. Right now there's no government, so I can understand how they might not be able to plan things. But nevertheless, we're hoping to coordinate with some of our colleagues. MITRE in particular is working on this NERDS Hat Creek experiment. NTIA, I still think, is intending to do an East Coast propagation experiment. It's just a question of when they kind of get to it. And then we're planning a flagship experiment for this coming year. It'll probably be kind of similar in probably the July-ish time frame is my guess to last year. Ideally, we're going to hold this at NASA's Wallops Flight Facility, and NOAA is right next door there at Wallops. So it'll be a very interesting spectrum environment. We have some work to coordinate this, but the people involved over the years have said they were very interested, and now we're just going to have to try to pull them in and get a plan in place. So overall, this is going to be a really exciting year for SpectrumX Flagship 1. And now you get to hear about what's been going on. Thank you. All right.
All right, so I'm going to talk a little bit about the experiment that happened this summer. So this experiment took place at the VLA, the Very Large Array, which is located in New Mexico. For those of you in the room, and I guess online as well, hands up if you were there. Yeah, so just from the folks in the room, and I know there was just probably more online, we had pretty significant participation. We had 24 people spanning undergraduates through senior faculty at this experiment, and there was, not 24 all at the same time. They just kind of overlap across the week that this experiment took place. But we had SpectrumX members as well as participation from NTIA, NRAO, which was our host as the organization that operates the VLA, and MITRE as well. So we had multiple sort of sectors represented as well as different career stages. It was a really diverse and talented group, and I'm really grateful for everyone's participation, which made this a successful experiment. So what did we do? The experiment had two pieces. One was a passive component where we wanted to get a snapshot of what this 7 gigahertz band looks like at the VLA site right now before any changes to allocations. So that was a campaign where we went around to different locations and we took passive measurements sweeping across the band and just recorded what there was to see, which honestly wasn't very much, but that's okay. We just wanted to see what was there. And the second piece was an active experiment. One of the candidates for moving into this lower 7 gigahertz band is 6G cell service. So we wanted to take a look at what that would look like to the VLA if that in fact becomes reality. So Ali, where's Ali? There you are. Ali led the active part of this experiment and did a really nice job coming up with both a recorded waveform, a 5G cell phone waveform that formed sort of the core of the active transmit experiment, and then several beacons, which you can see in the top of the spectrogram on the slide. And so on one of our days, on a maintenance day for the VLA, we put a transmitter in a car and drove it around. You can see where we located our transmit locations around the VLA kind of triangle shape there. So 2 stationary locations and 1 mobile experiment where we drove the car up and down the road, the public road that goes right through the center of the VLA. And so during this experiment, we had both mobile experiment platforms recording at different locations around the VLA site and the telescope itself, because the key was to look at what is the effect on science data from a simulated 6G cell phone driving around the site. So that was what we did, and we wanted to also engage students, and we certainly achieved that. Hands up if you were a student who participated. A couple of you here, yeah, okay. All right, so I just want to wrap up by saying that data upload to SDS is ongoing. It's been a great way to shake out the ability to put very large data sets on SDS. So that's ongoing, and thanks to the folks in the room and online who are helping with that. We're going to be using that data for the student data competition, so you get a chance to work with it, even if you didn't join us at the VLA. There's a number of papers that have been submitted and others are in development, and we're checking in on those on a regular basis to try to make sure we get a decent number of publications out of this. Data analysis is ongoing, both map data and VLA telescope data. And if you're interested in getting involved in experiments like this, speak to me at some point during this meeting. Let me know. I can add you to our experiment planning meeting if you really want to dig down into the details of how we put these experiments together, or I can just sort of keep your name on a list for when we do field experiments in the future, like the one that Frank mentioned. So with that, we're going to move on to our work element lead updates. We're going to go through everybody who's a component of Flagship 1 and let them give you a very short 5-minute update on their progress to date. Okay, so first up is Nick Rainville.
All right, well, I'll start with a very brief overview of what the mobile experiment platform is. So the idea here is that we have a very high performance SDR combined with edge AI ML compute and a custom analog front end that's really tuned for the type of observations, the type of experiments that we want to make for spectrum sensing. And the idea here is to have a flexible platform for spectrum monitoring, propagation, coexistence experiments, so transmit and receive experiments. So thinking back to the last center meeting, last spring, we were really at a point where we had a lot of equipment in a box that was a development platform. We accelerated pretty rapidly through this last 6 months or so to turn that into a usable instrument. So going into the summer, we started having our first real users, so thanks to all of you. And that led to the VLA experiment, where again, we had a team of students using half a dozen maps out in the field for the first time. So that was a success. We collected what's hopefully some pretty useful data out of that. But even more so than that, we had the first users that were hands-on. And so we had a lot of feedback from that first experiment. That's going to be driving us forward through this next year. So we didn't stop there. We actually deployed another map at the Powder platform. That's going to be there for long-term use and also to help us build out this next stage of development. Again, anybody that was there this summer experienced kind of the bare bones implementation of the map. People were using, command line interfaces, really going down pretty low level to get things to work the way they needed to. That's not our long-term vision. Long-term, we're going to have a much more evolved user experience. I think Randy's going to be talking about that a bit more. And so really, as we go through this next stage, it's about making the instrument more usable, more capable, but also just more refined. So somebody who's not an expert can kind of sit down, use it, focus on the experiment rather than the instrument itself. So looking forward, again, we're going to be working a lot on the map software capabilities and also just presenting the work we've already done. So going into the winter, we have some presentations as well at a couple different conferences where we're going to be kind of exposing the map to the world. And again, hopefully we get those Git repositories released as well, so we can make this something that can be replicated by used by more people. So that wraps it up from my side. We're going to take questions now or just do it at the end? Okay.
Randy.
All right.
Next,
You gotta get
fantastic.
us to lunch.
All right. My name is Randy Herban. I'm a software engineer at Notre Dame, and I have the honor of taking all the wonderful scripts that Nick and others have built that control the individual various pieces into the map and trying to bring it together into a nice cohesive interface and just building it into something that can be more readily usable and not just here hop to a command line and start hacking away at things. So they've done a fantastic job of getting the pieces working individually and now bringing it into a nice web interface. which is kind of tied into, and we call it the sensing platform. Part of it is the software running on the MEP itself to control the various pieces. Then a secondary server running at Notre Dame, which kind of sees everything and connect into it and do scans and control it and do stuff that way. So right now, the sensing platform is able to control the ring buffer, the RF sock, and the recording scripts, which are kind of the three main things in there. We're telling it to go tune to a frequency, start recording this, set it at the sample rate, bring data back, and start to visualize it. We have a copy of the web server running locally on each MEP, so that way when you're in a field and there's no network anywhere near you, you can still connect hotspot onto that device, get a feel for what data, what you're seeing, is the antenna hooked up properly, are we tuned to the right frequency, et cetera, and get a live feedback to say, yeah, we're doing what we expect to be doing. So I have some confidence that when I hit record and walk away, I'm going to collect data that I expect to. So we're also able to kind of quickly see the spectrograms and a waterfall in there, so you know, yes, I see stuff. Here's an example of several FM stations at Notre Dame. So we can see stuff. We're doing it and we're pulling it back and visualizing it as we expect to. With the VLA experiment, the goal was, here, let's just collect IQ, save it to disk, and do something. So now we're starting to be able to bring those individual pieces back, visualize it in a few different ways, and then move from there. The secondary half of this is, yes, now we know we can see stuff, but it's just on the disk. How do we do something useful with it? There's pieces in here to be able to say, hey, select this range of data, upload it into the SDS, and from there it'll be a whole the second half of visualizing and sharing and kind of processing the data. Every aspect of this is being built with experiments in mind. That is, I don't want you just worrying about tying into the web interface and doing the right things onto it. I want to be able to let you think about it from, what do I want to do when this node is in the field collecting stuff? I either want to tune to a frequency, collect some IQ data, do some uploading later, or I want to tune to some frequencies, do some quick signal processing on it, look for something interesting, maybe save snapshots of the data or some other transforms of it, and then when we get it back home, then do uploads. So we're kind of going with that experiment mindset of, here's what you want to do with the box, build you and give you the tools to be able to do that, and go from there. Thank you.
All right, thanks. David.
Hey, good morning, everyone. I'm David Pettifor. I work for the Center for Research Computing at Notre Dame, and my team is in charge of the SpectrumX data system. You've heard SDS mentioned probably a lot already this morning. So that's what this is, the data system and visualizations interface. So our goal here is to establish a large data store. It's more than just a glorified Google Drive. We have the ability to index your data. We know the RF data and digital RF formats. So we really are striving to make this a platform where you can share your information with multiple access levels, enable us as a community to do data exploration, discovery, and collaboration through structured data organization. We've got captures and data sets that you can create. And so the accomplishments that we've reached since the last center meeting, the data uploading and downloading is now live, and you can do this through both our internal SDK, our software development kit, if you're familiar with Python. You can also do this straight through the web portal, so you don't have to have any programming experience to be able to upload and download. Data set creation and sharing with multiple levels of access is also now live, and this is all available at our website, the SDS, so sds.crc.nd.edu, and then post-upload data processing with built-in waterfall and spectrogram visualizations, which I have an example up here. And so looking forward, we're targeting federated deployments of the SDS. So I know MIT is working on deploying an instance of this. All of our code is public and available. So if you'd like to pull this down, deploy it at your own institution, you can do that. And we're working again on this federated searching capability, to where if you're searching on one site, all of these satellite sites will also share that information. And so we can say, hey, if you're interested in this band, you might also want to check out maybe MIT's. They've got some data over there as well. So yeah, we will be, like Caleb mentioned earlier this morning, him and I will be at a table during the poster session. If you have questions, if you'd like to sign up or see demonstrations of how all this works, I will be there.
And the SDS will be the platform for the student data competition.
Yes. Yep.
You should repeat that.
The SDS will be the platform used for the student data competition. So students should probably get signed up for that. Thank you.
So,
All right, hello. Shen, I'm representing the Edge AI ML team. So just to refresh your memory, the goals of this team is, there are 4 goals essentially. Detecting, characterizing the RF environments, processing the metadata, identifying the RF signals, and capturing the emergence of events. Since the last center meeting, the team has been actually making pretty significant progress in pretty much the first 3 goals. The main accomplishments, first is the metadata processing tools, especially for sensing and targets. For the first 2 goals, this is mainly coming from Maria and Karen's team, who I believe Karen is online. The second is this deep learning framework that jointly detect and recognize wideband signals. Then this is mainly for goal 3. And this mainly comes from Daniela's team. And last is the shallow transformer signal detector, also for goal 3. This is mostly coming from my team. So let me just talk a little bit about each one of this. So for the metadata processing, essentially, we're basically hoping to understand the basically labels of the various components of the data that we're getting from the environment. This includes, for example, the sensor, where we want to know whether the sensor is functioning well. It's the antenna, the RF chain. What are the parameters? Are they functioning as expected? And this also involves the kind of the data labeling part, if you will, of the potential data that we're collecting. So this basically the targets and the applications. So the team currently has a workflow and making progress in several of these fronts. I think we'll have posters to talk the details about this, if I'm not mistaken. And in terms of the machine learning-based signal detection, we have developed this CV YOLO framework. This is to borrow some ideas from the computer vision, but utilize that on the spectrum data that we're having, with the goal of doing wideband signal detection in a more kind of efficient and more better performance manner. And the last one, which is utilizes shallow transformer, is really to try to push this to the ultimate goal of deploying this on the edge, because the machine learning solution that we first developed may actually be pretty large. So this would mostly be on the cloud. But if we want to really put it on the JSON and to put it on the edge, we need to shrink the size. We need to reduce the compute. So this is where trying to implement some of these shallow transformer-based solutions actually makes sense. The idea there is really to, instead of having a large model that you want to deploy on the edge, we're going to try to deploy a small model. But just like what we do in signal processing, that we may have a very weak signal detector, but we can iterative, basically by calling the same detector over and over again to gradually improve the performance. Here we're using the same idea, but on a machine learning model. So we're going to continue to develop this in the near future. Try to make the technique more mature, and so the teams have submit papers, and which I didn't include here, but that's all.
Okay, Sudhakar is next. Sudhakar, are you online to do your slides next?
Yes. Did you want me to? Oh, yes. Okay.
Yep, go ahead.
Oh, thank you. Can you guys hear me?
Yeah.
Okay, so I am Sudhakar Pamarti, a faculty at UCLA. So we were primarily working on the radio Houndex portion of this thing. The goal is to basically generate, come up with next generation spectrum sensors, which have very low swap, very low size, power, and cost things, right? So part of that thing was to come up with the reference platform designs that Frank's group at MIT was taking care of, and I believe they are complete. The remaining part of it basically was to see what parts can we integrate more effectively to cut down the cost. So a big chunk of our goal was to integrate the wideband RF tuner and the local oscillator, which count for a huge portion of the front end's power, size, and cost, right? And the second goal was to identify research problems that we can take and go and get some additional funding from other sources and so on. So roughly speaking, the first task, that's what we've been primarily working on, developing this populous prototype. The status, we are about 80% done with the schematic design and about 10% done in the layout. That is where we are. Since it's a wideband tuner, the goal is to get really good harmonic rejection when you're mixing a passband signal down to baseband and suppress a lot of the blockers. So top left is a figure that is a simulation result. There is a full core circuit simulation at transistor level. It takes about 2-3 days to run. And you can see the local oscillator about 200 megahertz, and see everything suppressed to better than 66 dB, stretching all the way up to 9 gigahertz or so. So we are currently continuing on this thing, trying to tape it out either next month or the month after. That's that one. That's the main one. The second one regarding identifying potential interesting research problems and avenues. Arjuna at FIU and we came up with this idea of replacing the traditional way of full band digitization and then doing DFTs or other signal transforms. We thought of replacing that with an approach of analog transforms followed by digitization. People have tried this in the past, but there are many problems with linearity and mismatches. We have a way of addressing both the linearity and the mismatch problems. And this promises about 600x lower energy than the conventional way. So this approach could be really interesting for the lower end versions like Radio PopX and so on. We still need to discuss this thing, see where we can send it and so on. So that is all I have for today. Do you have time for questions now or later?
We're going to hold questions till the end.
Okay, thank you.
Thanks. All right, Laila.
Okay, I'll try to be quick and not hold you for lunch. So basically what we are developing is a platform where you can have flexibility. It is a phase array with a bunch of channels that basically you can replace or the antenna or the RF front end, so that you can make experiments in like an interference suppression in all of the domains, the propagation domain, the analog domain, and in the digital domain, and see how they cascade. So basically, this is a portable 16-channel, as you know, transmit and reception. They are like a full duplex. So you have two different apertures, one working with, I don't have like the details of the RF front end here, but you have a 16-channel data converter that goes to a 3.5 to 7 gigahertz band up conversion with some amplification, so that we can achieve the requirement of minimum EIRP. And also we have an antenna, broadband antenna design, all of them like connected in one big Pelican case, where we have like a lot of like thermal challenges and integration and sturdiness problems to solve. Not problems, let's put challenging. Here you can see what is the prototype, the drawn prototype. Here you can see the antenna. Basically here you can see 3 Vivaldis that are stacked to increase gain in the elevation, but we have like to keep all of the channels separated, so then we can perform some digital beamforming and synthesizing some nulls to see how much this nulling functionality that will improve the signal to noise and interference ratio. What more? We also have the challenge of designing this up and down conversion as linear as we can, so we can isolate exactly what would be the benefits of some nulling or some gain, like an antenna gain or phase array gain. What more can I tell you? Also, the mixer, like the up and down conversion, it has to be wideband, it has to be tunable and with a low phase noise characteristics. So we have to keep all of the downstream of the signal very, very clean. Some of the advance that we've done so far is we have the boards all connected. Cabling calibration are done. We are also with the smaller mock-up in CBRS frequency, just because we are working from CBRS to 7.8 up conversion in the anechoic chamber, doing over-the-air calibration. We have some modulations already programmed. We have the basic beamforming networks algorithm implemented. What more? Yeah, we're almost with the full demonstration around the corner. And yeah, we're lucky to have a bunch of amazing students that are working. We have to split our team because we have many disciplines to tackle. So we are so lucky to have them. They are super dedicated. And yeah, I'm happy to give you more information, timeline, and all of the details. I hope that we can have a platform that other colleagues, they can implement their algorithms and they can use to test changing antennas, changing RF, analog filter, interference suppression approaches. And yeah, also the basic, we are working with initial instantaneous bandwidth of 160, but this specific data converter, it can accommodate up to 1 gigahertz instantaneous bandwidth, so we can implement some MIMO experiments. Yeah, it's a real a neat approach. Thank you, Frank, for giving us the chance to work on that. And yeah, I'm happy to answer any questions later on. Thank you.
All right, I think Mike is online, hopefully. Okay, go ahead, Mike.
Yeah, hi. Yeah, okay, so now for something completely different. This is with regard to policy. So, the motivation here is to try to relate what's being done in hardware, software, and so to have some ultimate policy impact. This is really an effort with myself and Randy and Dongning, sort of working together on a few different aspects of this. So I'm just going to talk about sort of a more high-level stuff that we've discussed. Really, we want to provide guidance for potential experiments, which may or may not, will hopefully have policy impact. That's the goal. And we also want to maintain the awareness of the evolving policy landscape, which is becoming seemingly more challenging. So, what we've done, I guess, is summarized in some memos. This is originally motivated by what's going on in 7 to 8 gigahertz. And so there's one memo on outlining what's going on there and what we might do in terms of interference measurements within that band. But given the new administration, it's not clear how how the relevance should be weighted at this point. Another memo, which is what this figure is referring to, is the potential for, so the original motivation is kind of, does it make sense to have spot markets, where you have different incumbents that are offering different kinds of services, but may want to pool their spectrum and offer it into as supply into a secondary market that a service provider might be able to tap into. And so, the idea is, well, could there be a pooling agreement among the incumbents, for example, in 7 to 8 gigahertz, which allows the secondary service provider at the bottom to compensate the incumbents and while controlling interference to the incumbent clients. So, there's been some work on pooling, and by some of us as well that we're pursuing. Then there's another memo that we've written on. It's sort of work in progress on suggested experiment using beacons. I think probably Dongning will talk more about that. So there's a possibility, say, of doing these kinds of experiments with some transmission capability on the part of the MEPS to do beacon-assisted interference management, as well as experiments, doing experiments with interference, measuring interference where the MEP receiver is not co-located or not very close to the target location, which is the case in CBRS because you're trying to infer interference at the ship, given sensor measurements maybe on the coast. So this is something that we've been pursuing analytically and conceivably can be converted into an experiment at some point. So I think that's all I need to say. I'll hand it off to, who's it, Randy?
It's Dongning next.
Oh, okay.
Thanks, Mike.
Hi, thanks, Mike, for giving the sort of overview of this whole direction that we're pursuing. So I'm going to focus on this work element on design, modeling, analysis of beacon signaling and coordination. The goals here are to develop beacon signaling and coordination mechanisms there, and to also develop analysis methodologies and tools for hypothesis testing and evaluation using FP1 experiment results. So we are part of this is that we would like to hopefully inform on the experimental design of experiments, and maybe once data is in, that we'll be able to do some further analysis and hypothesis testing. So far, the main achievement is that we have developed a mathematical model for interference management based on sensors and beacons. We sort of have a formalism built to describe what are the signals we're interested in understanding using data collected by sensors, and how possibly we can use a beacon to transmit signals to inform those potential interference sources to maybe adjust their power or adjust their spectrum allocation in order to control the amount of interference that we wish to control, or we wish to mitigate. And so one example is sort of motivated by CBRS. So that would be the picture here that we have here a list of 16 sensors on the shore and a number of transmitters, and we wish to protect one one zone, protected zone somewhere that is further in the sea. And so we have we actually have a paper that is ready for IEEE ICC that put this in a sort of formal footing and propose a an exact algorithm that so it's suboptimal in some sense, but it's well motivated to be able to estimate the transmit powers based on what the sensors observe, and that is motivated by some maximum likelihood detection sort of theory, and we have some numerical results there too. So, and then main contributors here, so a lot of the detailed work is done by Swaroop Gopalam, that's our postdoc, and this is done within, mostly within Northwestern, with also colleagues Rennie, Barry, and Mike Honig. So that's all I have to say here. Thank you.
The last one, I guess there's a couple more, right?
Two more after you.
Okay, good. So, all right, I'm going to talk about the third task under the, I guess, sort of the policy bucket, which is on spectrum sharing for 7 to 8 gigahertz. And yeah, this, we started off in this thinking we want to understand, what was appropriate for the whole 7 to 8 gigahertz band, and think about the incumbents and possible new entrants. And as Mike and I think Frank even alluded to, this has been a bit of a moving target. When we started this flagship, the National Spectrum Strategy had identified 7.125 to oh, no, I've got that wrong. Had identified, I don't remember the exact, but 7 up through 8 gigahertz as, a band of interest. And so we started looking at that band, looking at the different incumbents within that band. And then with the more recent Big Beautiful Bill, really restricted the focus on a sub part of that band from 7.125 to 7.4 gigahertz, which is now where the interest is, and actually explicitly removed 7.4 and higher from consideration. The other thing is that the focus there became on auctioning for high power cellular. So, I think if one likely scenario is that band gets auctioned and all of the incumbent microwave links and things in it get moved, and then sharing is sort of not really a high priority. And so that is one aspect. There's also interest in Wi-Fi, using the lower part of this band to expand the 6 gigahertz and enable them to have more wide Wi-Fi channels. I think and so there is some discussion there in between Wi-Fi and cellular for at least part of 7 to 8 gigahertz that we're thinking about. Sharing between the two of them hasn't been really discussed here. There are things in Europe that's being discussed for the upper 6 of sharing between Wi-Fi and cellular. So that is possibly something we could look at as well. So that's sort of we've been tracking and thinking about sort of what's going on in this band. And as I said, it's a moving target. The other thing is I think just thinking about sharing in general that may not apply to the lower part of the 7 gigahertz, but may apply in other settings, and maybe we can still do experiments that inform sort of sharing in a broader sense. Things like beacons that you just heard about could be relevant there. One of the things that I indicated here is also this idea of using spectrum agility and being able to bundle different bands of spectrum and move between them as a way of making shared spectrum more valuable for commercial use. So this is this idea that it's actually out there now where a given commercial band could be used as supplemental coverage, and when it's not available, you could shift your traffic to your primary bands, right? And so if you could take this to an extreme where instead of having one supplemental band, maybe I have several of these, and depending on when they're available, I can shift my traffic around. And you can show that by doing that, you can sort of make your these bands more valuable to a provider that's trying to offer some type of guaranteed service. And so we've been thinking about doing this in the context of 5G with Igor. and a student and trying to think about simulating these, and then possibly, is there an experiment that could be done there as well? And so I'll stop there.
Thanks. Ryan? Traffic management.
Yes. Hi, everyone. I'm Ryan Volz. I'm a research scientist at MIT Haystack Observatory, and I'm the lead for the data and metadata work element. So this work element kind of ties together a lot of other work elements, and you'll see the team members are basically pulled from a lot of the other work elements in this flagship project. Our goal is to specify requirements and formats for data and metadata to enable interoperability between the different FP1 work elements and the external community. And basically, we decided we don't want to reinvent the wheel, so we're using existing data formats like our digital RF format that we already used at MIT Haystack, and the external SIGMF format, which is broadly used within the community and has been used by other spectrum folks like the NTIA in their kind of platforms. So 6 months ago, we barely had data collecting on the MEP, and now I can report that we have data, we have lots of data, and the MEP is really working really well, and we're recording digital RF, and not only are we getting that IQ data in digital RF, but we're also outputting spectrograms now. That data has been flowing into the SDS, as you heard, and the MEP sensing platform, and the FP1 teams have gained a lot of experience in using these formats now. And 6 months ago, people were aware I was talking about digital RF, but they didn't really know how to use it. They've gotten a lot of experience using it now. And so I think we've got some experienced MEP users that are working with these formats. And now we're looking forward to digital RF 3.0, where we're going to take some of that experience and build it into a next generation data format that will tied together a lot of the ideas and work better for cloud computing and the SDS. So on the right, you can just see a figure that I threw together that kind of shows what the data looks like on the MEP. We shove everything in a ring buffer directory. We have data directories with spectrograms that are images. You can see one of those on the right, and you've seen some of those in a few of the other talks. We have data sampling at different sample rates. And within that, you have the IQ data and then also spectrogram data as separate data formats. And those can get uploaded to the SDS. And more recently, even just last week, we've started being able to live output our spectrogram data over MQTT messaging into the sensing platform. And so now we can actually, instead of trying to run a GNU radio live while we're using the MEPs to try and see what the data is, we can actually flow it into our platforms now. And we can see a demo of that down with the poster session where we have a MEP set up. So come talk to us down there. And that's really all I have.
All right, and last up we have Nikos. Nikos online? All right.
Yes. Can you hear me?
Yep, go ahead.
All right. Thank you for having the patience. I know I'm between you and your lunch. So quickly, I've been working with my team on reliable communication in interference-limited scenarios, including adversarial scenarios, such as jamming. And the work we've been doing under Flagship Project 1 is proof of concept demonstrations, primarily using Powder, as well as our own lab equipment. To remind you a little bit about the technique, this idea of being able to operate reliably in the presence of what would otherwise be annoying interference was hard to believe a few years ago, but it is quite simple, and it is based on subspace intersection. So in the simplest form, if you transmit a certain packet twice, and the packet encounters different interference during these two transmissions, and if at the receiver you use at least two receive antennas and down conversion chains, what you can get is two subspaces. The first subspace is spanned by the packet of interest, which is the orange little vector here, and some interference, right? So you get a subspace which spans the subspace spanned by these two signals, and then the second time you get a different subspace. The key idea is that these subspaces intersect at the signal of interest, and therefore you can recover by algebraic means the signal of interest, no matter how strong the interference is, and no matter what is the nature of interference. It can be analog, it can be digital, it can be a jammer, and this actually works in practice. So we did a lot of work, particularly in the spring and also in the summer, with powder experimentation. I don't know how many of you have worked with powder, but it takes quite some effort to learn how to use these tools and remote, let's say, transmission. Part of the reason is that you don't have, let's say, you don't see the environment where you are operating. You don't really know things like, how far away are the transmitters. For a while, we were thinking we were operating over the air, but turned out that the two software radios were connected using cables, actually cables to the wrong ports. So we were receiving our secondary transmission, which is supposed to be low power, basically through crosstalk, through leakage. And we were able to decode it. So it took quite some effort. We were the #1 user of powder for several months in the spring. But we succeeded in demonstrating this technique works at 2.4 and 5.8 under different kinds of interference, and for two scenarios, narrowband transmission and wideband transmission, or more wideband transmission, I should say, 5 megahertz bandwidth using OFDM type signaling. This is work done primarily by my student Spiros Pepas and my other student Paris Karakassis. Our main progress since the last center meeting, we had papers at ICASP and transactions on wireless communications, actually joined with Daniela from UCLA. The student passed his PhD proposal defense. We made major progress towards a variation of this scheme that is repetitionless. So it turns out you don't need to repeat. Obviously, repetition reduces your transmission rate. So it turns out you don't need to reduce your transmission rate by much, only by very, very little. And we demonstrated this not only in theory, but using software radios in practice. Finally, we began work for outdoors demonstrations, initially using USB-powered SDRs and laptops. And we hope to get to the map after some time. So thank you for your attention, and hope you have a great lunch.
Yeah, so thanks to everyone in the session for keeping your presentations nice and tight. We got in about 55 minutes. So I think maybe we can have 5 minutes for questions.
Sure.
All right, are there questions? I don't know how to get out of this. Are there questions on anything that you just heard for Flagship 1? All right, I'll finish just by saying that we've pulled a lot of these threads together in the big VLA experiment we did over the summer, and we're hoping to do the same, but even more, and pull even more of these work elements together for our flagship experiment that we plan to run next summer. So we're going to be focusing on the beginning of planning for that at the workshop on Wednesday morning. So I hope to see many of you there to help us define what that experiment's going to look like, and we're going to try to make it a great experience for everyone who can attend. Thanks.